Hello, let's work in this new tutorial. So now we're addressing transition to turbulence, probably the most elusive problem in transition modeling in CFD. So here I already have some results. So see the dots here are the experimental results, and then we have different simulations. So see that we're running Laminar. DNS in theory, so see that it is correlating. So basically just to explain that what we have here in the experimental results is that first we have a trend here that is going to laminars, and then you have to laminar flow, and then you have the onset of the transition to turbulence, and then it switched to turbulence. Just to frame a little bit also the problem that we have the classical flat plate. So see that have this flat plate, the flow incoming, and then there is some region that the flow is still laminar, and then you have the onset to turbulence, and that you see here in the experimental. So see that one simulation using the laminar or DNS, you have the feed towards the laminar solution, then running the purely SST, fully turbulent. You have it here also is fit into the turbulence solution, and then we are using two other transitional turbulence model, and see that they managed to capture that transition to turbulence. So what I was saying, that it's very elusive and it's very difficult to capture. So since that to resolve transition to turbulence, you need verifying measures that you have y plus less than 1. Also, you need to be careful when imposing boundary conditions. So we're going to address that in this case. So you need to give boundary conditions here, and you need to give some variables, but you need to let the decay of that turbulence intensity, so you have the right decay here, so you can capture the proper physics. So it can be elusive, difficult to resolve. And one thing that use a transition modeling only if you know that the physics that you are solving requires these kind of models, because it can be really difficult to get the solution and requires verifying measures. So this case, by the way, this case that we're doing is the classical flat plate. Is this have it here? Is this, for instance, you have this solution, the Lee-Saki solution. See that we have this flat plate DNA solution, by the way, is this one, and see that you have the flat plate, the rounding. And what is interesting in this solution, that here in this you can find this PDF in the internet, that you have here also the same values, and see that you have the laminar solution, the turbulent solution, and the onset of the transition. This is just to stress that this is a DNA solution. It's an extremely fine measure. If I will recall, it's like 1 billion or 2 billion cells to get that. So you see here the advantage of using turbulence models, just to enforce that idea, why we want to use turbulence models, and just to show you also the solution. So here we're just working at 2D case, but basically we're doing this coupling, and you have the solution here. So and let me put it here, and see here that you have laminar, then you have the hotspots and all those waves that are growing, and then you have the full onset of the turbulent flow. So basically this is what we're trying to model. Okay, here what you're seeing here is will be the full DNA solution. So let's work in this case. So you can download, you will have the results, experimental results. Also you have it in the data files in the website. And let us work. So if you go to the turbulence tab, so we're very familiar already to this tab, so I will go straight to the turbulence tab. So here you have all the turbulence models. So for instance, see that you have the K omega, you have different variants of the K omega. So the standard one will be this one, okay, the SST, and see that you have this option. So you can enable this intermittency transition model there. So we address this in the lectures, okay? But you have different models. So for instance, you have also the transition SST, that for this case probably is the one that's giving the best results. So see that you have this one, the cyan line here corresponds to the transition SST, to the SST with the intermittency equation, and then the blue one corresponds for equation that we have as we address in the theory, the intermittency plus the boundary layer, the momentum boundary layer. So let's work with this model, but then you can just try it out the other one. So to set up this one, just select this one. You have, as usual, as we addressed in the previous lectures, different corrections for address those deficiencies that you have in the models. And now we go to the initial conditions. So when it comes to the initial conditions here, it's pretty much the same that we have done so far, but now as you go to the inlet, you will have a new one, which is intermittency. This is the new equation, that it will define, as we addressed in the theory, that when you have a value of 1 means that you have fully turbulent flow, and when you have a value of 0, you have laminar flow. So when you do the post-process, you can identify close to the walls which are the laminar or turbulent regions. But what is important of this is that, as I told you, that you need to give the right boundary conditions. So when it comes in the inlet for intermittency, you need to give it 1. So in the inlet, it have to be fully turbulent. Why? Because you want this intensity to decay, and when it arrives to the walls, okay, you should have, approximately speaking, you should have the right intensity, turbulence intensity. So if you put here 0, it means that everything is laminar, and it might happen that you will have your solution will try to go and fit to the laminar solution. Actually, it's not. It will. That is what will happen. And maybe we are going to see that. Okay, so in terms of just go to the theory, you have the Fluent manual, and here you have a little bit the correlations that you use. So see that there is playing here, they give you this correlation for the decay of turbulence intensity. So as you see here at the inlet, you set a high value. Sometimes those values that you will need to set at the inlet, it might happen that they are very unrealistic or very high. But the problem, the idea is that they are high because when it arrives to the wall, you need to have the right intensity. Okay, this is the model. Within the models, you have this decay, and you need to have the right decay. So let's set up here. So always in intermittency, set up to 1. So these two values that we have here, they correspond to the actual experiments. Okay, so if you go to the Saki or the T3A aircraft tech experiment, you will have this value. So you set up this one, then in boundary conditions, the rest is a standard, just the inlet, then you have the outlet as we have done so far. So then let's move here, okay, in this vertical workflow. So we go to reference values. So we are normalizing here. So the length of the flat plate, or what we call this tool, but here where it doesn't matter, we can use these values for getting the friction coefficient, okay, that we're plotting here. Then we move to methods. Okay, so let's use the standard method, but again, you're feel free to play with all the methods, but for steady solutions, usually the couple is the best one, is the most robust one. Then in report definitions, set up the standard report. So this is a practice for you. So for me, usually what I will set up is an integral quantity. So in this case, I'm computing wall shear stresses average at the wall. Okay, then the Y plus average at the wall also, and the drag coefficient. Okay, I will monitor these 3 quantities because also we have monitors, but usually these monitors, they are not also a very good indication that you are converging or now. Okay, so see here that at the beginning it's a little bit misleading how you see these residuals, but then it will go down. But it's better to monitor some internal quantities. So we keep working here. So register, nothing to do, initialization, and let's initialize the solution. I will use the values that are coming from the inlet. Okay, so see that we have all these values. We wrote the scripts in lecture 4, okay, a small program, so you know what is going on here to get your initial conditions. Okay, so see that everything is initialized as 1 as turbulent, and at this point we're ready to run. Okay, so let me go here. I will press calculate. So here we're running the fully transition solution. Okay, the models, I see that we're solving 4 equations. So the K omega plus the intermittency and the red theta, the one that boundary layer momentum sickness. So we address this in the theory. I won't go into details. So this is relative fast solution. So just going back to the DNS. This is DNS what requires 1 or 2 billion searches, something like that. You can imagine that it's very expensive. It took like probably 1 month, a lot of computational resources, a lot of contribution to global warming, now running those supercomputers. So now running this intermittency model, okay, in a few iterations, probably like let's run up to 150. You will see here that this monitor, the intermittency, won't go down. It will stay flat. This is not a problem. Just check this order that they are going down, and always check your internal quantity. So see that they are not oscillating much. So this is an indication that you have reached a statistically steady solution. Okay, so let's go to 200, and we're going to stop it there. Okay, so at this point we have a solution, and let's do the plotting. Okay, so you go here, XY plot, and I want to plot the solution on the wall of the flat plate. So what we want to plot is the screen friction, and I already compute here a custom field function, is the Reynolds numbers in the X, okay, based in the length of the flat plate. So as you go here into custom fields, let me show you how it's computed. It's just very straightforward. Density, velocity, and length divided viscosity, the standard definition. Sometimes be careful also when computing this Reynolds number in your reference system, okay? So if you have negative value of X, it might be a problem, this Reynolds. So in my case, I know that where the flat place to start is 0. So be careful of that, okay? So just have that in mind. So now that we have this, we have X-axis, Y-axis, okay? So you plot the 2 axes. So by default in Fluent, you will have this enabled. So disable this one, and then you can choose the second axis. Okay, and says plot, and we have the plot here, and see that we have, and what is happening here is that you see in arriving to the leading edge, it's going like this, and this is correlating to the laminar solution, low skin friction coefficient. But then at one point you will have the onset of the turbulence transition, okay, of the transition, and then it goes from here, boom, it jumps, and it goes turbulent. But what is important is also you need to capture well where this onset happens, because sometimes you can use some turbulence models, or you can go on and for a DNS, and probably you will overpredict or underpredict where happens this. So now let's compare with the experimental results. So I will load a file. I have it here. So I will load this one, Reynolds X plot, and see that we have a fairly good agreement. Okay, so the red line, it will be the experimental, and it's fitting very well my experimental results or my numerics. So this is transition, okay? So let's rerun this case, but now just to show you what happened. But so you go laminar, you will see that this will fit to this one fully. If you go turbulent, it will go here and will stay here as I showed you at the beginning, okay? So what I was mentioning also during the lectures, that have in mind that CFD solutions, okay, the fully turbulent models, okay, the models that do not address transition to turbulence, they fit very well the forced transition simulations or turbulent solutions, okay? So sometimes this happens with airfoils, that you can have experimental data, and sometimes that data can have natural transition or can have forced transition, and usually CFD simulations tends to correlate better to forced transition. So have that in mind. So if you run the SST, KX, and whatever spiral models, they all will resolve this one very well, but this area will fit here in the upper part, telling you that everything is turbulent, which all those turbulence, they assume that your boundary layer is fully turbulent. So but it was mentioned that let's rerun, but let's choose the run turbulence intensity level at the inlet, and let's see what happens. So let's go into the boundary conditions, and I will choose here at the inlet, and let's choose 0, okay? And then initialization, so I'm telling that everything is laminar, and let's see what happens. Okay, everything laminar, compute from inlet, see that everything is 0, go and let me iterate. Okay, so let's see what happened. So let's see where it will correlate. So also this is a part of transition to turbulence that it may happen that these models also are very sensitive to initial conditions, to these parameters, intermittency or the theta Reynolds, okay, the boundary layer thickness, momentum thickness, Reynolds number. So let it run and let's see what we get. Okay, I arrived to 200 iterations. I will stop here. You see that my residuals, all these quantities are well converged, except for intermittency. This is usually the one that is difficult to converge, but it's not a problem. Then also remember that you will monitor your convergence rate using some integral quantities like CD or wall shear stresses. Okay, here you have my Y plus. So remember that transition to turbulence requires very low Y plus, below 1. Do not go below 0.1, okay? You won't get much improvement, but it definitely have to be below 1. And let's plot the solution, okay? So what we have in this case, and let's see what we get. Okay, so in this case, okay, I'll plot this one. Okay, so if we compare with the previous one, you will see that the onset, it is under predicted. So let me go, and I think I have the previous one, the transition with the right values here, and see the difference that the experimental, then the transition is still the one with different values, but you see that the onset, the transition point is different. Okay, so you see that you have this influence. But let's go now also choose another turbulence intensity level. Okay, so I will go to inlet, and now I will choose something a little bit high. Okay, this was interesting. So let me put here 1, and now let me show you the influence, okay, of the turbulence intensity. So we have this value, and let's put everything turbulent, and let me put a high value here. So a high value here means that when the flow arrives to the flat plate, to the leading edge, probably will have a value that it might be too high. Okay, so remember that it's computed using this correlation. So let's use that value. Initialization, inlet, I will initialize here. So see that you have your values initialized. Let's run again, 200 iteration will be enough. And let's see what we have. Okay, so I arrived to 200 iterations. You see that my integral quantities are well converged. They are not oscillating, plus my residuals also, they have a nice behavior. So let's plot again shear stresses on the plate and see what we have now. Okay, so it's clearly that this is very different from the previous one. So see here that now by using a intensity, turbulence intensity too high, see that it will correlate to the fully turbulent flow as we were expecting. So as you see, these turbulence models are very sensitive to your initial conditions of turbulence intensity and intermittency. But in general, the practice will be, remember that intermittency at the inlet, you should define it as one that everything is entering is turbulent, and then choose a acceptable level or a level that it will give you that decay, and when it arrives at the inlet, you will have the right turbulence intensity. Okay, and the post-processing, let's go. I haven't showed this the case, so let's plot. So this is the velocity. So see that you have here the flow entering, reaching the leading edge, and then the development of the boundary layer. So in this case, the boundary layer, you don't have separation or laminar separation bubbles. In the next case that we're going to do, we're going to see those laminar separation bubbles. But what is interesting to see here is that if you go in turbulence tab, you will access the intermittency field. And as you plot this one, this is the one that is telling you where you have turbulent or laminar flow. So see that we define these boundary conditions where everything is turbulent, okay? And see that where you have blue region, blue means laminar. So see that all this region is laminar, so it's a large boundary layer. And then you go back, you will see that now it becomes turbulent, or you have what you see here, blue is the viscous sublayer, okay? But this is what it's telling you, okay? So see that you have that region here, okay? So this is the idea, or this is what is behind these models. Let me change the branch here, okay? And again, we can check also the turbulence intensity. Okay, you can, oops, okay, I want the whole flow out to range, sorry. Okay, so see here that at the inlet it was entering this level, and then it decays, and when arrive here, arrive with a different level. Okay, so this is important that you need to set those values. Okay, so this was for this case, and the next one will be a little bit more practical from an airfoil, and we're going to see the laminar separation bubble. So hope you enjoy. Feel free to play with this case, and see you next time. Bye.